Hey guys, here are our notes on Newton's third law. Newton's third law can be very confusing, so try to take some time to really look over these. First of all, Newton's third law says that forces always act in pairs, meaning if I have a force on one object, there must be another force on another object somewhere else that is equal in size to that force and opposite in direction. Now, it's the same type of force. It's always going to be an interaction. It's an action and reaction between two objects. So, for example, if I push down on the desk right now, the desk pushes back up on me with an equal force. Now, I'm the one that feels the force. For example, if I run into a wall, for some reason, I'm probably going to be the one getting hurt, not the wall. That's because my mass compared to the wall and everything that the wall is attached to is much smaller. So I am going to experience a larger acceleration, and the acceleration is what we can see as the effect of the force. Here are some examples. We have a guy pushing against the wall. He's pushing with 100 newtons. Now, some of us have trouble understanding that inanimate objects can apply force, and this wall is inanimate. It is pushing back with 100 newtons. We have a guy on the earth. This is the really hard one, okay? The action is that the earth pulls the person down. That's easy. We can see that all the time. You jump off something and you're going to fall due to gravity. However, you are actually pulling the earth up with the same amount of force. Now, compared to the grand scheme of things, the earth is so big that your little gravitational pull isn't going to affect it at all. That's why we accelerate down towards the center of the earth at 9.8 meters per second. The earth is not really going to accelerate. It's so big. Now, in this example, we have a guy pushing the ground, so the ground pushes him forward. That's how we walk. We get propelled forward because we push back on the ground. And I gave this example in class. If I was trying to run on ice, I'm not really going to go anywhere because there's not much friction. I can't actually apply a good force to the ground so that it will push me forward enough to move. Same idea if I were in space and there's nothing to push against. I can't push back on anything in order to go forward. When you swim, you push back on the water, and the water pushes you forward. Hey! Sorry guys, I had to pause my video for a second. I don't know where I was. Action, reaction, talking about gravity. Just understand that those forces are equal and opposite. Same idea with shooting a gun. The bullet is going to experience the force a lot more than the gun, even though they are giving off the same amount of force. But the bullet experiences a much larger acceleration. So here we have a hammer coming into interaction with a nail right here. Anytime you touch an object, you cannot touch without being touched with the same force. So the hammer applies a force to the nail applies the exact same force in an opposite direction to the hammer. Now, how does the nail actually make it into the wall or whatever you're trying to hammer? Well, there are external forces on the hammer, such as your hand, allowing that to happen. Now, just thinking of this, we are going to go ahead and I'm going to work a couple examples from our worksheet that we were looking at. Okay, this is page 8 in your unit. It is worksheet 2, looking at interactions. So here we have a person pushing a system of blocks. We have block B and block A. I'm going to draw a separate free body diagram for each one, and then we're going to look at the forces between B and A and the forces that create Newton's third law pair. Here we have an interaction. Anytime you have an interaction between two objects, anytime they touch, you're going to have a Newton's third law pair. If we look at B, B has a force of gravity and a normal force. Now the normal force is due to the floor, so I'm going to write a floor here. Those are equal to each other. Because it says constant acceleration in this direction, that means all of our forces pointing to the right for each object must be greater than the forces pointing to the left. If we look at these forces, we have a hand is pushing on the object to the right. So I'm going to put F push here. We also have A is resisting B. A is pushing back on B. So this is the force of A on B. And then we're sliding across the floor, so there's probably a force of friction on B as well. Now here I've just drawn 2 arrows in that direction. You cannot draw 2 arrows like this. Okay, they have to be beside each other. Now if we look at A has a force of gravity, points straight down, and there's a normal force on A from the floor. Now if we look at what is touching A, well, B is pushing A to the right. This is F of B on A, and there's probably a force of friction for A as well. There is not a force of the hand acting on box A because the hand is not pushing A, only box B is pushing A. So now we can look at our free body diagram and figure out Newton's third law pair. Newton's third law pair is equal and opposite. So these 2 forces they represent the interaction. So this FB on A has to be equal in size to A on B, and it has to be opposite in direction. Notice the way I've drawn these. This one points to the right, this one points to the left. So they create a Newton's third law pair. One thing that is important when you're looking at a Newton's third law pair is that you always draw the forces on different objects. Okay, like these 2 forces could never represent a Newton's third law pair because they're only on one free body diagram. These 2 forces, however, are on separate free body diagrams, so I can at least start to think that they represent a Newton's third law pair. Okay, let's look at 7. Number 7. How does the force block A exerts on block B compare to B on A? Obviously they're going to be equal, but just think about that wording. A on B, B on A. A hammer hits a nail, the nail hits the hammer back. That's what Newton's third law is saying. Action, reaction. So here we have a constant velocity. That means everything's going to be equal. If we look at B, the rope is pulling B to the left, so I'm going to call that a tension. Now right here at the hook is where we have an interaction. B is pulling on A, that's our action, so our reaction is that A pulls back on B. So box B has a force of gravity and a normal force. Those are equal to each other. And then there's a force of friction on B, probably to the right. And A pulls back on B. So F of A on B. Now if I look at A has a normal force and a force of gravity. And there's probably some friction on A. And we have B pulling on A. So F of B on A is how I'm going to write that. Now, these 2 forces are equal in size and opposite in direction. So they create a Newton's third law pair. And just look at the wording. This is where the interaction is happening. Now, just because we have the force of friction and tension here, those are not a Newton's third law pair because it's not the same force. Okay, this is the force of the friction due to the floor. This is the tension due to the rope. But both of these are both due to the fact that those 2 objects are touching. So that's an interaction. Alright guys, I hope this helps just a little bit. Helps you finish your worksheet and completely draw free body diagrams. Have a good weekend.